Last time we discussed Calogero-Moser model with rational potential, quadratic external potential, and in the end of the last lecture, I showed you the formula which is analogous for free motion in the space of matrices, which we studied in detail when we discussed the rational Calogero-Moser model without external potential. And in this more general case, we should consider the following matrix. Where X naught and L naught are matrices taken at the initial time, at time equals 0. This matrix can be diagonalized, where this X is X of t, diagonal matrix with diagonal elements are coordinates of the particles as functions of time. And V is the diagonalization matrix, which is defined up to multiplication by a diagonal matrix from the right, and this D is diagonal. And this freedom can be fixed as usual by the requirement that the vector E, which is whose components are all equal to 1, is preserved by this matrix. This condition allows us to fix this matrix D. The proof and the statement is that these eigenvalues as functions of time move as Calogero-Moser particles in the external potential. You see that when omega tends to 0, this is the frequency of the harmonic oscillator in this external potential. When it tends to 0, this matrix becomes the familiar matrix which we discussed before, whose eigenvalues move as Calogero-Moser particles without external potential. I'm not sure that it would be useful to present this proof in detail. The proof is very similar to what we did in detail in the previous case. And let me leave this problem for homework. If you have difficulties, then you can see the lecture notes which appear on the site of our Skaltiach site. There is this proof in some more details. Okay, so, and the last statement about this is that if xi of t is a solution to equations of motion for rational Calogero-Moser model without external potential, with omega equals 0. Then, from this statement, it follows that xi tilde, defined in the following way. We should take xi as and renormalize the time in the following way. And the corollary is that this x tilde move is as Calogero-Moser particles in the external potential. It immediately follows from this formula. And now let me pass to a more general model, to the trigonometric case. So soon after discovery of the rational Calogero-Moser model, other people found that this model admits a deformation, and integrability is preserved after this deformation. Now we consider the case when the potential, interaction potential between particles has a one period in the complex plane. So instead of rational function, we consider the Hamiltonian of the following form. Kinetic term is the same, but interaction is different. There is a parameter gamma, and it is clear that the period is gamma I divided by pi. Yes. This function is hyperbolic sinus function, but we will call this model trigonometric nevertheless. And it becomes really trigonometric when gamma is pure imaginary. If it is real, it is hyperbolic function. If gamma is imaginary, so the period is in the imaginary x direction, then it becomes usual sinus function. And in this case, the model can be interpreted as a model on the circle, and the particles move along boundary, along the circle, and the interaction, the potential, interaction potential depends on the distance between particles. So instead of the axis become just angles phi of the particle. When gamma tends to 0, we come back to the rational case. This potential becomes 1 over xi minus xj squared. Almost all statements and properties of the rational model have their direct analogues for this trigonometric case. However, their formulations and proofs may be a little bit more difficult. Some of them we will follow some of them. And I should only add that the property of self-duality does not hold for this trigonometric case. That the duality transformation which we discussed last time can be applied to this model, but as a result you get another model which is called rational Rusinat-Schneider model, and we will discuss it later. So the equations of motion are as follows. In Newtonian form, they can be written like this. This model, trigonometric, is sometimes called Calogero-Sutherland model. Sutherland. Sutherland considered, probably first, who considered this trigonometric model in quantum case, when pi are differential operators. But I will call this model just trigonometric Calogero-Sutherland model. It has a Lax representation. The Lax matrix has the following matrix elements. And to write down explicitly the M matrix, it is convenient to introduce, to pass to other variables, instead of x's, consider exponential functions of them. So in this, if gamma is pure imaginary, these are just complex coordinates of points on the circle. And introduce diagonal matrix whose elements are these new variables W. And introduce also the following matrices. And on the diagonal, we have zeros. This is nothing else than this guy rewritten in this new coordinates. And another matrix, B. and also diagonal matrix and in terms of these matrices, the Lax pair can be written in the following form. The problem for you is to prove that the Lax equation is equivalent to the equations of motion. Let me show you the equation the analog of the equation which characterizes the Lax matrix. This was in the rational case, this equation. And in trigonometric case, its generalization is as follows. In the limit, when gamma goes to 0, we obtain this. And writing explicitly matrix elements of the left-hand side and right-hand side, you get just this, the non-diagonal part of the Lax matrix. A few problems. Of course, as soon as we have the Lax equation at hand, we can write integrals of motion as symmetric functions of eigenvalues. Each eigenvalue is integral of motion, and usually the integrals of motion are taken to be traces of powers of the Lax matrix. And the first problem is to calculate this for k equals 2 and show that H2 is just this Hamiltonian. And also the next problem is to find H3 in the explicit form. The next problem is to prove that these integrals of motion are in involution. This is indeed the case, and so we can this proves that the model is completely integrable. It has n independent integrals of motion in involution. This formula gives infinitely many of them, but the integral when k is n plus 1, n plus 2, and so on, these integrals are already dependent of the first n for n particles. The next problem is to apply the projection method or linearization method to this trigonometric case and show that this W's move which are satisfy the equations of motion of the trigonometric model, they move as eigenvalues of the following matrix. So eigenvalues of this matrix as functions of t are just these W's, which are solution to the equations of motion. And the most difficult problem, the problem with a star, so to speak, is to generalize the statement to higher flows. So again, each Hamiltonian defined by this formula generates its own Hamiltonian flow with its own time, and the problem is to find a matrix whose eigenvalues move as these particles as functions of a higher flow. The next result which I would like to discuss belongs to Nikita Nekrasov, who proved in 1997 that the rational Calogero-Moser model in the external potential is in some non-trivial way equivalent to the trigonometric model in compact case when the particles are on the circle. So with imaginary gamma. And I would like to show you some details of this statement. In fact, this correspondence is not so explicit. So it's a difficult task to write explicitly how one variables are expressed through other variables. You will see. So let me consider imaginary gamma. And for trigonometric system, we define coordinates as theta I and psi and momenta psi I. These thetas are just angles. The particles are the unit circle, not unit with some radius depending on gamma, and theta i's are angles of each particle, and psi I are the corresponding momenta. They have canonical Poisson brackets. So in these terms, the Hamiltonian, trigonometric Hamiltonian, can be written like this. And L For the rational system, an external field, we will also change the notation and we'll denote the Lux matrix for this system as Pj is P. So the diagonal part consists of momenta minus. Now, and the coupling constant G is also pure imaginary in this case. So the interaction is repulsive, but the particle cannot go far from the origin because they are confined in the external potential. This was the Lux matrix in the rational case, and also introduce matrices Z, which is P plus I omega X, and Z DAG. The analog of the Lux equation, which we derived when discussed this rational model, can be written in this form. And in this, from this formula, it can be immediately derived that this matrix Z as a function of time is as follows. With some unitary matrix V. Let us consider, this is the key step of the correspondence, to consider the decomposition of the matrix Z in the product of unitary and Hermitian matrix. That's always possible. And this is an analog of representation of a complex number Z as module times exponent of I phi, argument. This R will become, in the extension, it will become a Hermitian matrix, and this will become some unitary matrix when we decompose matrix Z. And it is better to, it can be done in two ways, from the left and from the right. In one dimension, this is no difference, but in higher dimensions, when they are non-commutative matrices, there are two ways to write this Hermitian matrix from the left or from the right. And we will prefer the symmetric version when we multiply from both sides. Where R is Hermitian and U is unitary. Then, multiplying this, we can conclude that the product of Z DAG times Z is U to the minus 1 or U to the minus 1 to the 1/2. Let W be the diagonal matrix with the following diagonal elements. And consider the matrix V, which diagonalizes the unitary matrix U. So U is this product. And we fix the freedom by the same condition. Put L equal to V to the minus 1 R V, where R is this matrix. It came from rational model. And now we are going to obtain some elements which belong to trigonometric model. And this is one of them. This L will be a Lax matrix of the compact trigonometric model. So the commutation, this commutation relation in the rational case can be rewritten in terms of Z and Z DAG like this. Now let us substitute this decomposition into this commutation relation and use the definition of the matrix A. Then we can write it in the following form. After some transformations, it acquires the following form. But at this moment, we immediately recognize the commutation relation for the Lax matrix of the trigonometric Calogero model, which I wrote some time ago. However, on the right-hand side, we have omega here, but in that case, in that formula before, we had gamma here instead of omega. So the conclusion is that to identify the models, we should put gamma equal to omega. And in this case, this model become equivalent because this formula shows that it allows us to restore the correct form of the Lax matrix for trigonometric model. And the Hamiltonians of the rational system, which are traces of powers of product Z times Z DAG, become Hamiltonians of the trigonometric system. In particular, for k, if k equals 1, on the left-hand side, we have just the Hamiltonian of the rational model and external potential. And this one is just trace of L, which is sum over momentum, the total momentum. But this case, the equations of motion are trivial, or all particles move along the circle with constant velocity. So you see that the dynamics, non-trivial dynamics in the rational model in external potential, it appears to be equivalent in some non-trivial way to the free motion on the circle. This is rather unexpected statement, and so it is remarkable and needs requires some understanding. And the last step is to show that this transformation between the coordinates and momenta on the circle in trigonometric case and to coordinates momenta in the rational case is canonical. You see that this transformation is given in rather implicit form. Here, the key formula which determines this transformation. This is a decomposition of the Lax matrix of the rational model into product of unitary and Hermitian matrix. In general case, this is a rather difficult problem to write this transformation explicitly. So it is almost impossible to identify these models explicitly. However, it is possible to prove that this transformation is canonical. To see this, we should write the symplectic form in terms of matrices. Rewrite it in real coordinates and momenta. This formula is trivial. Just to substitute what is z and what is z dark in terms of p and x. And we should prove that the symplectic form of the trigonometric model is equal to the canonical form in the rational model. This can be done using the lemma, technical lemma, which we discussed, I don't remember last time or before. I remind you the lemma that the form with tilde is equal to the form without tilde with some correction. For any two matrices X and Y, and x tilde is similarity transformation of x, and the same with y. Using this identity, whose proof was left for you, you can prove equality of these symplectic forms, which means that the transformation is canonical. Now we pass to most general case, to elliptic case. It appears that the trigonometric Calogero-Moser model has further deformation with one parameter. Namely, when instead of potential with one period given by trigonometric functions, you can consider two periodic with two independent periods, potential function with two independent periods in complex plane. And this is just what is called elliptic. Any function with two non-trivial periods in the complex plane is called elliptic. So to consider this model, we need some information about elliptic functions. You're probably not familiar with this important part of theory of functions, and I should present some basic facts and introduce notation. Let us consider complex plane. And consider two linearly independent vectors. This will be called 2 omega 1, and this 2 omega 2. The origin of this 2 is a tradition. Notation adopted in some handbooks. I advise you to look at the Ahieser book. Which is called, it is in the list of literature in lecture notes. It is called Elements of the Theory of Elliptic Functions. It is a very good book, written in a simple way, easily readable, because it is written for engineers, without any high science, which is usually used in presentation for mathematicians. There are some other books about elliptic functions. You can see them in the list of references. So these numbers will be our two periods. So we can consider the fundamental domain. Consider lattice with these two basic vectors. So this is commutative discrete groups, translations to vectors of the lattice. And we can choose in some way the fundamental domain for this group. It can be chosen in different ways. This is just one of them. probably the simplest one. And consider functions which have these two periods. The famous Liouville's theorem states that any bounded function on the complex plane is a constant. So if we require that these functions are bounded, it immediately follows that they are constants. So elliptic functions must have singularities in the fundamental domain, and so in all other domains obtained by shift by periods of the lattice. So at least one pole, but it's a simple, easy to show that one simple pole is impossible, because the sum of residues should be 0. So one non-trivial simple poles is not possible. So the simplest possible situation is one double pole or two simple poles with opposite residues. And both these two cases are very important. Have special notation for them. These functions, I will show you some of them. And well studied. The first case, the second order pole, it is convenient to put it on the origin. So then in all vertices of the lattice there will be a pole. And this function, having this single double pole in the fundamental domain, is called Weierstrass elliptic function and is denoted by this strange letter pi, some version of pi, traditional notation. So its expansion around 0 has the following form. This is singular term plus g1 z squared plus g2 z to the fourth and so on. It's easy to see that this function is even. So the first, its property is this. So the expansion goes over even powers. It is periodic, two periodic, double periodic. And it can be defined by the following series. Where S is the element of the lattice with integer coefficients, or some linear combination of vectors of the lattice with integer coefficients. So this is a double sum. The naive definition would be without this term, just sum over all vertices of the lattice. By construction, this function is periodic, but the problem is that such a series doesn't converge. To make it convergent, you should subtract this correction. Then this series is already convergent. The proof, detailed proof of this, you can find it in the Hieser's book. So from this formula, it easily follows periodicity and this even, that the fact that the function is even. And this function, Weierstrass function, will be the potential, pairwise potential of the particles instead of 1 over x squared. So the leading part is just 1 over x squared, and these are corrections. Another important function is Weierstrass zeta function, which is defined as a primitive of Weierstrass function, namely in this way. It has simple pole at the origin, and it is not already double periodic, but behaves very in a simple way when we shift by periods. We will see very soon. The integral representation of this is as follows. Again, this subtraction is needed to cancel the pole, because otherwise the integral is not defined, because pi has pole at the origin. But this term cancels this pole, and everything is okay. And also it can be defined by the series. When we shift the argument by a period, it behaves like this. There is some additive constant here. And it can be proved that this eta 1 and eta 2 satisfy the following identity. This can be proved by integration. Suppose this is fundamental domain, and here is a pole somewhere inside of this function, and we should integrate this function along the boundary of this fundamental domain. It will give us the left-hand side of this identity, and the other way, equivalent way to calculate this integral is to take residue of this pole, and this gives the right-hand side. And there is a third important Weierstrass function, which is called sigma function. And it is defined in the following way. It is the logarithmic derivative of the sigma function is zeta function. So the integral representation can be written in this way. Or sigma function can be defined by the following infinite product. And the monodromy properties of this function are as follows. So when we shift by one of the fundamental periods, some multiplier arises, and this is exponent of some linear function of an argument, of the argument. By construction, this function sigma has zeros, simple zeros in all in the origin, and so in all vertices of the lattice. As it is an odd function. By the way, this zeta is also odd. And sigma is odd. And its expansion around 0 is of the form, the first term is just z with coefficients 1 plus O of z to the degree 5. Notice that the term z cube, which could be here for arbitrary arbitrary odd function, is absent. The next term of the expansion is z to the 5. This property sometimes it becomes very important if you expand some formulas with elliptic functions to see where they have poles and of which form. This property may be important. The Weierstrass functions satisfy a lot of non-trivial and beautiful identities. You know that from high school, you know that trigonometric functions satisfy some many identities. And for elliptic functions, the situation is much worse. The number of identities much bigger, so there is no possibility to remember them. However, there is a very simple logical way to prove them. If you see some identity, to prove it is very simple. I will show you in a moment. But to write such identity is non-trivial. As a rule, the identities which are to be proved appear now I tell about my experience that suppose I calculate something related to an integrable model with elliptic functions and obtain some equality with different expressions in the left and right hand sides, but the problem requires that they should be equal. So this suggests that there exists an identity. Because of this, they are indeed equal. And now, and after that, you can try to prove this identity. And the logic of such proofs are always the same. Suppose you have some expression with some functions on the left-hand side and on the right-hand side. And you need to prove that they are equal. The first step is to introduce function f, which is difference of them. The next step is to prove that the right-hand side as a function of z is double periodic, so elliptic, with some periods. The next step is to look at possible singularities of this function f. Because these functions f and g usually have some denominators, which can, at some points, vanish. So this is a candidates for poles. And the next step is to prove that f is regular. So to do this, you need to consider each zero of the denominator and expand this function f around in some neighborhood of this zero, possible singularity. And if you are lucky, all singularities cancel, and you obtain a regular expression. This means that there is no pole in this point. And you should verify each of them, each such candidate for a pole. So each case when some of the denominators of this expression vanish. As soon as you prove this, that it's regular, it immediately follows from this and from this. By Liouville theorem, it follows that f is constant. It remains to find the constant. Usually, it can be done by some substitution of specific value of z here, some point z naught, for which it is convenient to choose it in such a way that the right-hand side simplifies. For example, g vanished at this point. It all depends on the situation, so not always easy to see which point you should take, but as a rule, this works. And you should calculate this, the right-hand side at this point, and this will be just the value of this constant. This last step has some variation. When you cannot find such a point at which the right-hand side becomes simple and it can be calculated, it may happen. And in this case, some more sophisticated method can help. You can try to expand the right-hand side at some possible singularity, what we did when obtained this regularity statement. But in this case, we expanded up to constant term, up to z to the 0 power. So we found only coefficients in front of singular terms. But you can try to expand further up to the next term, which is constant term. And see what is the coefficient. And this coefficient will be just this constant. So let me show you some examples of identities. Some of them will be important for what follows. This one is especially beautiful. At last, I should say that there is another system of notation for elliptic functions, which is also possible, which is also popular, and you can find it in many literature. It is through theta functions. Theta function is defined by the following series. Suppose we have, let us mark 1 on the complex plane and some number tau, such that imaginary part of tau is positive. Then theta function is defined by the series. The sum over all integer numbers the series is converges very fastly because of this condition. You have exponent to some minus positive number, and the module of this positive number grows as n squared. So the high terms of the series are very small. The series is convergent, absolutely convergent for any z. And you can easily prove from this definition that the monodromy properties of this function are like this. It is periodic with period 1, and when we shift by another period, tau, some multiplier linear in Z appears here. Now I don't remember exact form of this. Not important for us. And connection with this Weierstrass system of notation is as follows. Tau is the ratio of omega 2 by omega 1. So instead of two arbitrary periods, omega 1 and omega 2, here we fix one of them to be 1, and then the other one is some tau. So then this identification follows. In fact, similar to trigonometric case, when we have two periodic functions, two basic periodic functions, sinus and cosinus. Although they differ just by a shift, it's convenient to denote them separately in this case. One is sinus, the other is cosinus. And there are two of them according to half periods. Along with periods, the half periods are also very important points. So this, and this. That is why the periods are denoted as 2 omega alpha. Then omega alpha are half periods. And in the elliptic case, one can introduce 4 theta functions according to the number of half periods. Basically, they differ by shifts to these half periods. So 1/2, tau over 2, tau plus 1 over 2, and the third one is 0. This function, which is defined by this series, in this notation is called theta 3. It can be shown that it has one simple 0 at this half period tau plus 1 over 2. And all other and it is an even function. It follows from this definition. And other functions are defined as shifts of this theta 3 by half periods, multiplied probably by some simple exponential factors. Among them, theta 1 is odd, and all other are even. But we will not use this system of notation. And elliptic functions can be constructed from these theta functions as ratio of products of the form, for example, like this. If points A, I are zeros and points B, I are poles. Then it easily follows from the monodromy properties that this function f of z is double periodic when the sum of all zeros is equal to the sum of all poles. Then it is double periodic, meaning that it is elliptic. This is the standard way to construct elliptic functions from theta functions, as using them as building blocks. But we will not use this system of notation through theta functions. We will use these Weierstrass functions in what follows. But I told you this because this system of notation is very popular in the literature. If you decide to look at some literature on the subject, you may find there theta functions. And the last thing which I should say is to show you degenerations of these functions. When omega 1 tends to infinity and omega 2 is fixed in this way, then the Weierstrass P function becomes trigonometric. But plus some constant. And zeta and sigma this is when one of the periods tends to infinity, this one. This is fixed. But the higher degeneration is to tend to infinity both periods. In this case, we should tend gamma to 0 in these formulas, and you see that they have just 1 over squared here, gamma over x here, and just x here. So you see that these functions correspond to this highest degeneration corresponds to rational model. These are trigonometric case, and in general elliptic case, we will have this pi function as in the potential term of the model. So the potential term will be of this form. So we'll proceed next lecture, next time. For today, I think this is enough. And next time we will discuss the elliptic model in some detail and start to consider Rosenard-Schneider models.